So the confidence interval is meant to compare an average set of data, measurement data, to a true value. The t-test is a statistical test meant to compare two sets of measurement data to each other. And so here we have two temperature probes that were sat in water for 1 minute. So these are seconds, right? Going down to 60 seconds. And measuring the same water, the temperature of the same water. And the question is, are they measuring the same temperature? If you just look at these measurements, you think, oh yeah, they're probably measuring the same temperature. And if you measured, if you took the average of these two temperatures for the temp probes, you would think probably they're measuring the same temperature. But let's try to compare them using a t-test. The first step to doing a t-test is first to use an f-test. Now the f-test is comparing the standard deviations from the two sets of data. So the f-test is really just a calculated statistic that then we compare to a table value. We've got the standard deviation of the first data set squared over the standard deviation of the second data set squared. Now, when you do this calculation, you should have the larger standard deviation on the top so that the F calculated value is always greater than 1. If you don't calculate the standard deviation for this data first, you might not know which is which, but I'll show you what to do if you just use the functions. Now, it might not be too hard to do this on its own without using the data analysis pack, but the t-test is a little more complicated. So let's use the data analysis pack for everything, okay? We're going to go up here to data and then go to data analysis, and we are going to use the f-test for to sample for variance, okay? Now, variable range 1, that's one set of data. Variable range 2 is another set of data. So keep in mind when you're using the f-test and the t-test, you need to have all the data points, not just the average and the standard deviations. Okay, so I'm going to select for variable range 1 the temp probe number 1, just like that. For variable number 2, I'm going to use temp probe number 2. Okay, and this alpha represents what's left over from our confidence interval. So if we're at 95% confidence interval, that's a 0.95 in a fractional number, right? 0.95. And the 0.05 is what's left over. This is going to be the default, so you should always be using that 95% confidence level, unless you decide you want to go higher or ask some questions about confidence. But you can just leave that default as 0.05, and that comes from that 95% confidence level. Instead of putting my output in a new range, I'm just going to, in a new sheet, I'm just going to put it in a new range and put it right here. And I'm going to click OK. All right, so it's going to put all of my f-test data right here. What it spits out is the average, right, or the mean of temp probe 1, the mean of temp probe 2, the variance. Now the variance is equal to the standard deviation squared. Okay, so just so that you know that. And then here's the number of data points that were present. Okay, so if you counted up all these numbers, you get 61. And degrees of freedom is the number of measurements minus 1, right? So we have the degrees of freedom of each. And then this is your F statistic. So this is the thing you need to pay attention to right here. Now, when you're deciding what the answer is, are these two standard deviations similar enough or not? Are they similar or not? That's the real question. So is the variance technically similar between the two data sets? Okay, that's the question that we're answering. You're comparing this number, this F statistic, to the critical F value. And so that you could find in a table, but it's nice that the data analysis pack will spit that out for you. Okay, what is the critical value? Let me show you how you would find this. If we needed to look this up, it would be using variable 1, which is in the numerator, goes across the top, and variable 2, which is the denominator, right, would go down the side. And here we've got the degrees of freedom for each one. So for S1, right, we're going to go across, and theoretically we'd go all the way over to 60 because we have 60 degrees of freedom here, and then we would go down to 60. Now, we don't have that number here, right, but that's another reason why it's super great that it gives you that critical value. Now, if your F calculated value is greater than your F table value, or critical, I'll say critical value, okay, which is from the table, so I'll do table, okay, then the two standard deviations are different, right? The two variances are different, okay? If your F calculated value is less than your F critical value, okay, or table value, right, then your two variances are similar. Okay, so if we look at these two data, here's my calculated value and here's my critical value, we can see that my calculated value is less than my critical value, and therefore my variances are similar. So here I'm going to say variances are similar. Okay. Now, just so that you can see what's going on here, if I select this temp probe 2 as variable 1 and temp probe 1 as variable 2, I just want to show you what that will output. Okay, so again, F test, okay, except now I'm going to make variable 1 temp probe 2 and variable 2 temp probe 1, okay, and I'm going to have my output range be a new range now down here, okay. So now you can see we get the same average. Variable 2 now is variable 1. So here's my 2.37, 2.37, 2.229, 2.229, right? Everything is just swapped. But what that means is now you have the smaller variance on the top and the larger variance on the bottom. So your F calc is less than 1. You can compare this to your critical value here, but it's going to have opposite rules. Okay, so it's easier to remember that if you get an F value that is less than 1, then you should just scrap this and redo it and switch your variables. Okay, so that's the plan. Okay, so I'm just going to delete this. Edit, clear. Okay. So now that we have an answer, right, to the question, is the variance similar between the two data sets? The variances are similar. Now I can do a t-test. Okay, so again, we go back to the data tab, and then we go to data analysis, and now we can go to t-tests. Now you want to use, you've got two samples, okay, and you want to use now the equal variances option. If you had found that your calculated F value was greater than your critical F value, then you would use the unequal variances. Okay, so let's use the equal variances because that's what our F test found. Okay, now again, variable 1, you just want to keep them in the same order right now. We'll see what happens when we do that. Okay, variable 1, variable 2, okay, great. Hypothesized mean difference. Okay, this is a new entry. We're going to use the null hypothesis. So the null hypothesis says, I'm guessing that they are the same. There is no difference between these two means. Okay, so that's the null hypothesis. And we may find that we will reject the null hypothesis depending on our t value. Okay, again, this alpha tells us 0.05 means that our confidence interval is 0.95, which is 95%. So you can just leave that alone. Go to the output range, and I'm going to keep that right there. Okay. So there's my t-test. So is the average temperature the same for both probes? That's really the question that we're asking. Okay. So we're doing this t-test, and you'll again find we get the average, right? The mean out of each one of these. We get the variance, same number as we got here. Okay, we get our number of observations. We get a pooled variation, which I'm not going to go into. There's our hypothesized difference and our total degrees of freedom. So you'll notice this total degrees of freedom is just the sum of these two things. If you use the t-test for unequal variances, you might have a different number than just the sum of the 2 degrees of freedom. This is the number that we want to pay attention to. And you might be freaking out because it's a negative value right now. But actually, the absolute value of this is what we need to pay attention to. It doesn't matter if it's negative or positive. Again, it's going to give us the critical value for one tail versus 2 tails. Okay, and if you want to compare to this table, again, we do not have 120 degrees of freedom. Okay, so we could go to infinite, right, and see that that's a 1.96, and you'll see that that's pretty close to what the 2-tail critical value is. So that's not presuming that we know one is higher than the other. It's checking on both sides of the temperature distribution to see if it's the same or different. Okay, so it seems like the 2-tail critical value is what we would get out of this table, and so we're going to leave that alone. Okay, so that's what we're going to compare to. Now, again, if my t-table, t-stat, okay, is greater than my t-critical, okay, or table value, right, then that means that my 2 means, the 2 average temperatures, are different, okay? Okay, so you'll notice a trend here. Every time your calculated value is greater than your critical value, it means they're different. If your t-stat is less than your t-critical, or tabulated value, then that means your 2 means are different, are the same. So if we compare these two together, and remember that this is an absolute value number that we care about, then our statistic, our t-statistic, is way greater than our critical value, which would mean that the 2 temp probes are different. So 2 probes are reading different temps. Okay, so they're not calibrated to each other. They are statistically different from each other. So a 2.229 versus a 2.375, those 2 temperatures are different statistically. Okay. Let me just show you what this would look like if I switch, right? If I want to get a positive value here, all I'm doing is switching which variable is which. Okay. So I'm going to go back to data. I'm going to go to data analysis. Again, equal variances because my F test found that the variances are similar, okay? And all I'm doing here is switching, C2 to C62, B2 to B62, right? And then here, I'm changing this here, okay? So if I switch which variable is variable 1 and variable 2, we get all the same numbers, except now we get a positive value. So that doesn't change the outcome, right? 18 is still greater than 1.9799, and our 2 temperature probes are still reading different temperatures. So if you get a negative value here, don't freak out. Just drop the negative value from the t-test. If you get an F value that is less than 1, probably switch them around so you don't get your rules mixed up.